Hello, my name is Lindsay Clemens and I'm with the University of Idaho. My topic today is DDT and its environmental history and future. Imagine that it's a bright, sunny spring. Flowers are blooming, the skies are clear, but you can't hear any bird song. It's very silent outside. There's no chirping, and there's no feathered wings in sight. This is the future that we very narrowly avoided in the late half of the 20th century. But how did it come about? What happened was that there was a molecule that was being used as an insecticide called DDT. Now, what is DDT? DDT stands for dichlorodiphenyl trichloroethane. But what does that really mean? In this case, DDT is in the lines of an organochlorine pesticide. And the organochlorine pesticides are very notable in the fact that they work extremely well to do their job, killing insects. But another notable thing about them is that they are very stable compounds and they'll stay in a system for a long time. See, this results in biomagnification. So you have a small amount of DDT in the producers, such as the plants, or it could get into streams and go into the algae. From there, you can have low amounts of DDT become large amounts by consumers eating them. Because DDT is lipid soluble and very stable, it stays inside of the organism for life. And so each time they eat more, they accumulate more in their bodies each time they eat. And so as you go up the food chain, you go to secondary consumers, tertiary consumers, the top of the food chain. Each time they eat more food, they gain more and more of the DDT. And once you get to the top of the food chain with birds of prey such as ospreys, peregrine falcons, and American bald eagles, then you can have some major reproductive harm happening. In this case, the most prevalent reproductive harm is eggshell thinning. And so when they have a lot of eggshell thinning, they lay their eggs and it doesn't harm them directly, but the eggshells are too thin to support the egg into maturity. And so from there, the population just plummets. Here's an example from Florida and bald eagles. So we can see DDT is introduced in 1947 as a major pesticide. And you can see that the number of nesting pairs drastically plummets after 1947. Until 1958, there's hardly any at all. This is very indicative of what DDT was doing back in the 1940s and 50s. Now, the paper that I want to talk with you guys about looks at this with American kestrels. And so they did two things. The first thing they did was they went into the wild and found kestrels, and they looked at the eggshell thickness and concentration of DDT in the eggshell. From there, they calculated at what percentage of normal eggshell thickness eggs started to break. The second part was they took some American kestrels and then they fed them a specific amount of DDE. And DDE is a metabolite of DDT, which means when DDT breaks down, it produces breakdown products or metabolites. And what they wanted to do was measure the thickness with a known concentration of DDE of the eggshells. Now, in order to determine how many parts per million, or the concentration of DDT in the wild kestrel eggs, they used gas chromatography. Now, gas chromatography is a fairly common thing, a fairly common use of machinery. So, gas chromatography, this is not the particular kind they used, but gas chromatography is fairly uniform across different models. So for here, what you need is a stationary and a mobile phase. So the mobile phase in gas chromatography is the carrier gas. The carrier gas is usually an inert gas like helium or nitrogen gas. So it doesn't react with what is being put into the injector port. So the mobile phase carries the mobile phase, which is the carrier gas, it carries what you inject in the injector port through the column. Now, in the column is where you have the stationary phase, usually silica gel or another thing. And so when you put when you have the carrier gas and it goes through the stationary phase of the column, it carries with it what you injected in the injector port, and it goes to the column oven. Now the oven heats itself up at a steady rate, and what you injected is liquid, and it vaporizes. Different compounds vaporize at different temperatures. And so the amount of time it took for this specific compound to elute is called the retention time. And this is detected by the detector, and then the spikes are recorded by the recorder. Now, this is a way in order to determine compounds and what concentration they're at. Now, the results from the second part of their experiment is right here, from feeding the kestrels the DDE. So we have the control as 0.171 millimeters and 10 ppm as 0.126. Now this is around 73% the thickness of the control. From the first part of the experiment, they determined that the thickness that eggshells start breaking at is around 88%. And they were finding that kestrel eggs in the wild were having around 30 to 35 parts per million of DDT in their eggshells. And so you can see that the amount of DDT is way past what eggshells start breaking at. So you can see that even a small amount of DDT just wreaks havoc on eggshells and the populations of the birds that lay them. So what we really need to realize is how large of an effect using the smallest amount of DDT has on an ecosystem. Now, in the past couple of decades, the World Health Organization has authorized the use of DDT in places like South Africa in order to stop malaria. Now, in these instances, DDT is not being placed on plants, it's being placed directly in your house. And so what needs to happen is we need to remember the past of how DDT and what we need to do is remember the past of how harmful DDT can be to an ecosystem. And we need to do more studies on ways to use DDT in ways that are less harmful to the ecosystem. And also, we need to do more studies to find more alternatives to DDT, because DDT is very effective, but it's also very dangerous. Thank you. If you have any questions, I would love to answer them.